Here we'll go through a simple example of how using constcast in C++ can lead you into undefined behavior if you're not careful. So we'll start out by defining a constant integer a, which we'll set equal to 1. So this, because of the use of const, is an immutable value. It can't change for as long as it's in scope, and the compiler will enforce that. So if we wanted to define a pointer to a, we would have to do it like this. We would have to define a pointer to a const integer, b, and set it equal to the address of a. The reason we have to put const here is that the compiler needs to make sure that b can't be used to change the value of a. And in fact, if I had left out the const here and only included the star, this would throw a compiler error. But there is a way that you can try to get around this. And the way that we can try to do it is by taking the address of a, whose type, remember, is pointer to const int, and using the constcast keyword to forcibly change its type from pointer to const int to pointer to int. And that's reflected in the type of the output here, which we'll again call b. Now, at this point, we've got a non-const pointer to a const object, which means we've got a pointer, b, through which we could, in principle, try to change the value of a, which is supposed to be immutable. Now, this is, of course, a bit risky, but it should be okay as long as we only try to use b to access the value of a. If we try to use b to change the value of a, that's going to lead us to undefined behavior. Before we do that, though, let's print out some values to the screen so that we can do a before and after comparison later on. We'll print two rows of information, one detailing things that we get from A, the other detailing things that we get from B. In the first column, we'll put the address of A and the value of B. These should be the same, and we can see that they are. Now, every time that we do a run, we're going to get a different number in the first column. The important thing is that the first and second row entries should be the same. Next, we'll output the value of A and the contents of B. These should also be identical, and they should both be equal to 1, and we can see that they are, so no problem there. The third column only contains an entry for A, and that's the contents of the address of A. Now, you might think, why do we have to output this? Because surely the contents of the address of A should always be equal to the value of A. Well, wait and see. Well, now we've gone and done it. We've set the contents of the pointer b equal to 2. This is the same as saying a equals 2. If we had tried to say a equals 2, the compiler would have thrown us an error, because remember, a is supposed to be immutable. But because we used constcast to remove the const qualifier from b, we can actually do this, and it'll let us get away with it. So this is where we've tried to change an immutable value using constcast, and this is going to lead to undefined behavior. So now let's take a look at the effect of what we've done. I've repeated the same two output lines from before down here, and this is where you will find the output of those two new lines. You can see that there's been a change, and it's kind of difficult to understand. We can see that the address of A and the value of B are still the same. They should be, because we didn't try to change that. B is still pointing to A. But notice that the value of A is no longer the same as the contents of B. And since the contents of B is the value that we find at the address that B is pointing to, that's to say the address of the value of B, that's tough to explain, because we can see right here that the value of B and the address of A are the same thing. So these really should be the same, but they aren't, and that's hard to explain. Furthermore, you can see here that the contents of the address of A are no longer the same as the value of A. This is the kind of thing that you can run into when undefined behavior creeps into your code. So it's something that's well worth avoiding. Here we have the exact same code, but this time we've run it on Microsoft Visual Studio 2022 instead of on CoderPad. So this is going to be using a different compiler. The output is in the inset window right here. And notice that the output is different. Here the contents of the address of A are agreeing with the value of A rather than with the contents of B. We're getting 1 instead of 2. So 2 different results from the same code run through 2 different compilers. This is exactly the kind of thing that you can expect from undefined behavior, and this is why you want to avoid it as much as you can. And in fact, certain flavors of undefined behavior in other contexts could easily produce 2 different results from the same executable running on the same computer with the same inputs. Well, at this point, we've done what we set out to do. Just a couple of afterthoughts. I decided to try adding a little bit more to the CoderPad version of this. A couple of void functions that take an input integer and print it to the screen. One of them takes the input integer by value, the other one by constant reference. So they should produce exactly the same result, but if we call them with A, our constant integer that's been messed with via undefined behavior, as the argument, you can see that the first one, which passes by value, prints out 1, and the second one, which passes by constant reference, prints out 2. It really shouldn't be doing that. Again, undefined behavior giving us unexpected results. Just as an end note, by now there are probably at least a few people who are wondering if constcast is so dangerous to use and can lead you so easily into undefined behavior, why is it even there? Well, there are in fact a few edge cases where you might need to use it, and I've tried to construct a hypothetical example just using some pseudocode. I don't know how realistic this is, but it's the sort of place where you may want to consider using constcast. Suppose that you've got a code base, and there's a function here in the code base that's at the bottom of a long calling sequence. And one of the arguments here is a pointer to an array of constant floating point values, which we'll call P. This could be something like, for example, the const version of the data pointer from a standard vector. And suppose furthermore that in the course of maintaining the code, you suddenly discover that you need to include a call to some function from an ancient library, some old C math library perhaps that goes way back to the 1980s, that was coded up without const correctness. And it's expecting that pointer P to be a float pointer without the const. Well, I suppose that one thing that you could do would be to remove the const from the declaration of P up here at the top, but then you'd probably have to go all the way up the calling sequence and change it in every function all the way down the line. And that could turn out to be a nuisance because there might be places in this function or in that calling sequence where there might be function calls that expect P to have that const added to it. And if you try to change this by removing the const, these might start to throw complaints at you. Now, really, probably the best thing to do here would actually be to start passing the whole standard vector down the train by reference instead of passing just the data pointer. But if you really want, for whatever reason, to keep passing the data pointer, well, one solution would be to pass down both the const and non-const versions, but that'd be kind of ridiculous. If you're absolutely certain that the ancient library function isn't going to change anything in the data pointer, then you might want to constcast it to a float. Again, I wouldn't say that I would consider this to be the ideal solution, I would probably want to try to put something better in, but if you're in a tremendous hurry, which could very well be the case if you're understaffed, this might do the job. So it's never going to be the ideal solution, but it might turn out to be the lesser of two evils.